Hello, everybody. So today we're going to be talking about that ever so much central topic to statistical mechanics, the partition function. So the partition function is going to help us describe the structure of a given configuration of uh, energy states in a chemical system. So one of the first things we should keep in mind is last time we talked a lot about how likely certain configurations were, and this was dictated by the weight of the configuration. However, it turns out that very few configurations tend to really dominate the structure of a system. And oftentimes, only a single configuration or two is really going to dictate the structure. So, what we're going to want to do is try and identify what the most probable configuration is going to be, and then use that to describe what the structure of that configuration looks like. So, what we can do is start by thinking about how you try and determine the most probable anything. So, if I'm looking for the most probable configuration, it should have the highest weight or the most probable weight, which can always be determined by just taking the derivative of our weight, or in this case, the natural log of our weight, because both of these should be equal to 0 when we're at the most probable state. Now, trying to express this is a little bit tricky, and we often do this through the notation that um, the most probable weight, the sum of the change of the weights with uh, with changing configuration for each configuration should end up being 0. So essentially, that if I sum up any increases of weights or decreases of weights as I move the particles around, those should essentially end up being 0. So essentially, if I change the particle structure, the weight shouldn't change at all when you're summed up over the whole system. This should help indicate that you're in the most probable system. You can also think of this as just splitting it into the sum of the change in weights should also be 0, which should hopefully make sense from a multivariate calculus perspective. However, we also introduced the idea we have to apply several constraints, most notably fixed number of particles and fixed energy. So essentially, we're looking at an isolated system. And you can apply some mathematical tricks for by applying a closed system at a fixed energy. You can actually determine the proportion of particles in any state I uh, compared to the total number of particles via an exponential expression. So the percentage of particles in state I will be dictated by an exponential of a arbitrary constant alpha minus beta times the energy of that state. So this should start to seem familiar, as we've already noticed this before, where the probability of being found in a given state is going to be dictated by the energy of that state. So we can go ahead and, instead of having a subtraction and an exponential, we can separate this out into two exponential factors. And this is going to allow us to kind of rewrite the probability of our state. However, what we're going to want to first do is try and the probability of each state in terms of the number of particles in state I versus essentially the total number of particles, a an unknown constant value, and an exponential in terms of the energy of the system. However, now we need to find a way to essentially describe what my alpha and beta are and how they might be related. So one way we can do this is, again, by applying our constraints, because I know the total number of particles has to be equal to the sum of particles in any given state. So we can then input our previous expression for the number of particles in the state, and again, in terms of number of particles and the energy of the system. We know that the total number of particles and our E alpha should be constant, so that I should be able to pull them out in front of the sum with respect to states. So from here, what we can notice is that I've got n on the left side and n on the right side. Those two should be able to cancel out. And what I have is that the exponential of alpha plus the sum of our energy expression, when multiplied, should end up equaling 1. We can then rearrange this equation to solve for E alpha. So what we now know is that E alpha is equal to 1 over the sum of our exponential terms. So the sum of our states with regards to the exponential of the energy of the system times this constant beta. So this yields a net equation for the probability of finding a particle in state I related to the exponential of the energy of our system, of our individual state, over the sum of the exponential for the energy of all states. So this is going to be more commonly phrased as the Boltzmann distribution. So you've heard me use the expression a Boltzmann type distribution before, and it really regards this whole idea that the probability of finding a state in a system is going to be equal to this exponential. What I've been neglecting to talk about has been this fact that that exponential of the energy has to essentially be normalized by the probability of the sum of the probability of finding particles in any given state. And we can give our full Boltzmann distribution typically by writing it as the exponential of the negative of beta times the energy of the state we're examining over Q, where Q is the partition function, and again, is just pretty much the sum of the probability of the system being found in any of the individual states. So what we end up finding is that if I have one state who has a very high probability and everybody else has low, then this should have a probability near 1. If I have, say, a lot of other states with high probabilities, my probability of finding it in state I should drop much lower. So again, the partition function is really going to be a good description of how likely am I to find it in a state other than the one I care about. If I'm only going to find the state that I care about, this is probably going to be near this ratio should be near 1. If I'm more likely to be finding the system in other configurations, it should be a very large number. So again, one of the other things we now have to worry about is I still have one last variable left here, and that's beta. So if I get beta, I should be able to derive my partition function, and from there, be able to derive the likelihood of finding a particle in any given state, and thus any given energy value. So this we actually do have to kind of go to experimental data. So we can try and fit our partition function to experimental data, such as the ideal gas. And to a certain extent, we've already done this when we did the kinetic gas law. And from there, it can be demonstrated that beta equals 1 over kT. And while this holds for the ideal gas, it also holds for any number of other systems, including such systems as solids, liquids, you name it, beta is pretty much constant. So we can, it's very cool to demonstrate that the likelihood of being found in a state is going to be based on the Boltzmann constant and the temperature. Two simple parameters, when combined with state energy, is going to give me a lot of information about how likely I'm going to be able to find the system in any given state. So again, this also helps demonstrate a lot of phenomena we've seen already, most notably that temperature really controls the likelihood of being found in a state. If we take a look at the probability of occupying our state, if I have a high temperature, I'm going to only tend to occupy low energy states. Or if I have a low temperature, I only tend to occupy low energy states. If I have a high temperature, this partition function kind of goes nuts, and it lowers the probability of finding it in any individual state as more and more states of the ground state, as more and more states become available. However, one of the things I want to emphasize here is that this is with regard to the probability of finding a system in a given state. We often think about energy levels, however, and it turns out that many states are degenerate, which is another way of saying that they have identical energies. So we can actually include this degeneracy to turn our partition function from describing states, where I describes states, to where I describes energy levels. Where GI is going to be the number of degenerate states or structures that have identical energies of EI. So we can then turn our equation into describing probability of finding the system with a given energy or in an energy level by using the degeneracy of the system I'm examining times the exponential of the negative energy of that level over KT, all divided by pretty much the same partition function, but now written in a notation that's a sum of energy levels instead of states. So one of the things that this really helps show is that we can tend to favor energy levels that are higher in energy than we would normally think, as long as they have a high degeneracy. So if I have a highly degenerate energy level, even if any individual state is unfavorable, the energy level as a whole can become very favorable due to this extra factor. However, we can also use our expression for the probability of an energy level to give the relative probability of two energy levels. So let's say I'm in state I, and I want to figure out how likely I am to be in energy level I versus energy level J. Well, you can essentially split this out into the idea of taking our probability of being in energy level divided by our probability of being in energy level J. Then you can expand this into our full form of the probability of each energy of the energy level I divided by the partition function times the partition function divided by the energy level of probability of being in energy level J. Then the two partition functions just cancel out, and you can actually find the probability, the ratio of probability of being in state I to J using the degeneracy of each of our energy levels and the energy of each of these energy levels. However, let's be honest, this form of the equation is a little bit unwieldy. So what we can do is use a ratio of the degeneracies and then use our exponential rules to pull the energy of J up into the exponential up top by essentially subtracting the energy level J from I. So essentially a high separation of energy is going to tend to lead to if energy level I is much higher than J, this is going to make this state very improbable, as we'd have the negative exponential of a very large value. So I'd be very unlikely to be found in that high energy state unless degeneracy is able to help rescue me. However, if I'm looking at energy states, the degeneracy for each of those states should end up canceling out. So this would reduce our relative population to just being the exponential, the differences in energies. Now, one of the biggest take homes I really kind of want to emphasize about this is that it really indicates that what's controlling the relative populations of species in any given energy levels or states is going to mostly be controlled by two key factors. The stability, the inherent stability of those states, as is described by what their energy levels are, and the temperature of the system. The temperature of the system is going to make it a little bit easier to occupy higher energy systems, as it dampens this unfavorability due to the exponential term. However, low temperature is going to mean that I'm going to be in the lower energy state. So this is a little bit much to take in. So next time we're going to try and work some specific examples of looking at these relative probabilities. Until then, take care.